Time we were talking about the input resistance of the inverting amplifier, right? So this was the inverting amplifier configuration that we were talking about, and we wanted to calculate the input resistance. So what is the input resistance of any op-amp circuit? How is the input resistance of any op-amp circuit measured in practice here? So in practice, you would, or of any circuit, you have a block here, box with two terminals. If I want to know what is the input resistance of this circuit, how would I measure the input? I think your bag is here. So how would I measure the input resistance of this circuit? Yes, the bag is interesting, but I think we can. How would you measure the input resistance of this circuit? Yes, how would I do that? It's given? No, it's not given. How would you measure input resistance of a circuit? You have a circuit. You don't know. You want to. It's a block. It's a black box. What is the input resistance to any circuit? You put an ohm meter. But what is an ohm meter here? Sure. What is an ohm meter? How does it measure the resistance?
You put it on
by counting
parallel to
the electrons moving. Whoa.
How would you measure? Yeah, it's a nice. You put it parallel. So what does it do? What does an ohm meter do? Does an ohm meter have a resistance in series?
No.
I mean, obviously, it's going to be, if you put it in parallel with two terminals. If you open one terminal, it's not going to work, right? So it means current is flowing, right? Some current is flowing. So if current is flowing, and this circuit is not powered, it's because that ohm meter has inside it an ideal voltage source. So this ohm meter is, that measures resistance, is basically an ideal voltage source that has no series resistance. It's just pure ideal voltage source. If you have a pure ideal voltage source, somehow, you have a pure ideal voltage source, it's going to push current into this block. Why is it pushing current into this block? Because there is some impedance of this circuit, an equivalent impedance, right? Some equivalent impedance. This equivalent impedance, I will measure. This is something you're measuring, and that's what you do with the Thevenin equivalent. Yeah, very similarly, right? So the R Thevenin is what do you do? You short all the supplies. This circuit happens to have no supply, right? Assuming there's no supply in the circuit, of course. Because if there's a supply, it will ruin this measurement, right? So, but if you don't bring a resistor, you cannot measure a resistor value using an ohm meter while it's in the circuit. You can measure the voltage across it using a voltmeter, not an ohm meter, right? There's a difference there, right? But you can, and how does a voltmeter work? Voltmeter, you put it in parallel, but what is it going to do? It's obviously going to draw current, but the voltmeter, in that case, will be like an infinite impedance. It will be a device that has a very, very high impedance, so it will draw very little current. So this very little current, apply current divider rule, you will know the value of the resistor that you're putting in parallel, right? So or the voltage across the resistor that you have in parallel, right? If you draw a little bit of current, and these two devices are in the same parallel branch. So if you have a resistor here with current flowing through it, and I put another one in parallel here, then some current will flow in here as well, but the voltage across these two is the same. So this is like a voltmeter. But you don't want to draw too much current because then you're going to affect your circuit. Right? So this is a voltmeter. And this is a ohm meter. Ohm meter is an ideal voltage source. Ideal voltage source meaning this resistor is almost zero. Pretty much zero. The series resistance on the source is zero. So ideal voltage source doesn't have an internal resistance. There's no internal. And if it does that, then if you measure this current and you know this voltage, then V divided by I is equal to R. Right? So that is the internal impedance of any circuit. So this is now my circuit. Right? What am I doing? I'm applying an ideal voltage source here. Current is flowing. These divided by each other is going to give you the resistor R. We can know what it is by looking at the circuit and understanding the behavior. Because I have feedback, we know that these 2 points are virtually connected. So the voltage at these 2 nodes is the same. Assuming the gain is very high, the voltage here is 0, hence the voltage here is also 0. So this current is going to be due to this voltage applied on this resistor. So this, in this case, is the input resistance. Right? Okay? What did we find last time? We found that the gain of this device is equal to minus R2 over R1. If I want a high gain, what does this mean for R1? Small, right? So if it's small for practical values of R2, otherwise I have to put giga ohms for R2, right? So it's going to be small for practical values of R2, right? So if that's the case, that means this is one of the drawbacks, possible drawbacks of this configuration. That has a low input impedance. Do I want that? No, I don't want low input impedance, because if I have a low input impedance and I have a sensor here, am I drawing a lot of current from the sensor or little current from the sensor? A lot of current, right? If I have low input impedance here. So ideally I want a high input impedance, so I don't load my sensor, right? So this is a drawback of this configuration. So how do we deal with it if we still want an inverting amplifier, right? So circuit designers came up with this circuit. So let's see how this circuit operates. Okay. So this circuit has feedback as well. So it has a feedback loop. So some connection between the output and the negative terminal. So this is negative feedback, right? So this is still negative feedback, right? So if I have negative feedback, what does this imply? It implies that the voltage between these 2 nodes is the same. Here it's 0, meaning the voltage here is 0 as well, right? Now, which means that the input resistance is still what? R1. The input resistance is still R1. Is this good or bad? I don't know. It's the same as before so far, right? That's the input resistance. But what made this a bad thing in the previous circuit was the fact that the gain of the amplifier was minus R2 over R1. That was the drawback. It wasn't the fact that the R1 was the input resistance. If I can make R1 big and not have that make a detrimental effect on the gain, then I'm good. Then I've solved the problem. Correct? That's our objective here. So did this circuit do that or not? Let's see what happens in this circuit here. So if these 2 are virtually the same voltage, so the current flowing here, I1, is equal to V over R1. This is this current here, I1. Sure. Where is this I1 going to go? It cannot go inside here because I have an infinite input impedance of the op-amp, of the ideal op-amp, so it's going to flow up here. So I1 is equal to I2. Sure. Then what? So since there's current flowing here, fine, then I have a resistor connected to ground, and I have a resistor connected to the output. I expect current to be flowing in all these branches, right? So I will do nodal analysis to find the voltage Vx. I will find Vx, and what we will find is that we will find an equation for I4 that will show that this I4 can be amplified by placing this resistor in parallel. So the previous circuit, we didn't have this resistor connected to ground, right? Because we didn't have this resistor to ground, the feedback, the output voltage depended on what? A voltage drop across this resistor here, which was R2 in the previous case, and this one, right? Now we will find that the output voltage here depends on what? Fine, this is current flowing here. It will depend on this and the value of Vx, right? So I will have Vx, I will subtract this from it, and that's equal to V output. Is it related to R1? A little bit. It may be a little bit dependent on it because of the current flowing here. The current flowing here depends on R1, right? The current flowing here depends. It's equal to Vi over R1. So this is also equal to Vi over R1. So there may be some dependence, but is this dependence going to be as detrimental as the previous configuration where R2, where the gain was equal to minus R2 over R1? That's the question. Or is this addition of this resistor going to allow us some flexibility in the gain of the closed loop amplifier such that even though R1 is a limited value to a certain, certain resistance, I'm still able to get a large gain, independent of that, right? That's the story behind this circuit, right? So now let's derive the equations that govern this circuit. Yeah. So first, so the first assumption was what we discussed. V1 is equal to 0. Since I have feedback, then this input here is at 0 volts. Since this input is at 0 volts, that's what the first thing says here. This is V1. 2? 0.2? Where? 0.2 here? Yeah, this is VI. Sorry, if I zoom in, maybe it helps. No, this is VI, this is V1. This is, yeah, sorry, the PDF is not great yet. This is VI, so this is VI, and this is V1. Okay. So now let's see. So the next step was we calculated the input current I1. We said that this is going to be equal to VI divided by R1. VI divided by R1. Okay with that? Since the voltage here is 0, it's VI minus 0 over R1. VI minus 0 over VI minus V1 over R1. So that's VI over R1. Next, what do? We said that I2 here is going to equal I1, since I into the ideal amplifier is 0. So I2 is equal to I1 is equal to VI over R1 as well. So that's the next step. I2 is equal to I1 equals VI over R1. The next thing we want to do is, okay, this I2 is flowing in here. I want to be able to calculate Vx. So I can do it in many ways, right? So I know the current flowing here. I know the current flowing in here. I know this voltage is 0. So if I know this voltage is 0, and I know the value of this current, right? So I know this is 0 volts, and I know this is Vx, which is what I want to calculate, and I know the value for R2, and I know I2, because I2 is equal to I1, and it's equal to Vi over R1, right? So I know the current, I know the resistance, and I know the voltage on both sides of the resistance, right? So I can calculate, sorry, I don't know Vx. So what's the current flowing through the resistance equal to?
I2.
I2 is equal to what?
Vx over R2.
It's, yeah, the voltage difference, right? It's 0 minus Vx.
No, Vx minus 2.
No, because it's going like this.
Oh, it's the current.
Yeah, 0 minus Vx. So 0 minus Vx
Over R2.
over R2, right? So I know I2, and I know R2, I can calculate Vx, right? So if I calculate Vx, then I can calculate I3, because Vx over R3 is equal to I3. And then if I have I2 and I3, I can calculate I4. And
So
what?
you just sum them, you'll find.
So basically, I'm going to sum them up. What did I do? I was able to increase I4. Increasing I4, remember I4, V output is equal to this voltage drop plus Vx. So it's highly dependent on the voltage drop across R4.
Then you can find V0.
So I amplified it somehow using this modification of the circuit.
So and now since you know I4 and R4,
Yes, we can go home.
no, if you multiply them together, you can find V0.
V0, yeah, of course. That's if you know I4, but not no. There's also voltage. You have to voltage divided. Here this, and Vx, this.
So Vx minus V0 over
So Vx minus minus I4 R4 is equal to V output. V output is equal to Vx minus I4 R4. Okay? The trick was we were able to increase I4 without what? Without increasing I1. Because if you increase I1, what does it mean? It means if you put a voltage, you have a small resistance and high current will flow, right? Which means that the input impedance of the amplifier is small. But I kept this, whatever I wanted it to be, large value. So I kept this large, but I was able to amplify the I4 going through R4 by using this trick, right? So
Can we multiply
V naught can equal what? We want to calculate V naught, V output, right? It's equal to what? It's equal to Vx minus I4 R4. What did you want it to be? V naught. What did you want to put on the left hand side here? Vx I4. But I4 we will calculate by summing up I2 and I3. I2 is equal to I1, right?
No, but
And I3 is equal to Vx over R3.
no, but if you use your method, you can solve for V naught as well.
Yeah, I mean,
We already
again,
know
with
I4.
circuits, yeah, I mean, I'm sure, again, this is, I told you, it will convert to a circuits problem, and circuits, you can solve them in many ways. So this is just one way of solving the circuit here. So, I mean, you can go around this, instead of going around this loop here, you can go around this loop, right? One here, one here, one
I
here,
was thinking of
and then
making R4.
0, right? This is 0 here.
I was thinking
Right, so
making R2, R4, R3 because there are Y connection to make it.
You can
delta,
convert
so-
Y to delta, yeah,
and
circuits.
then, yeah.
Circuits, yes, sure, you can do
make
that.
it one resistor
You
instead
can
of
do that,
this.
yeah. You can convert to delta and then it becomes like this, right? And
Yeah,
then the
and
volt
then I
and V
can-
output is equal to the voltage across this resistor only. Yeah, circuits, right? So you can enjoy your time, convert to delta star. Just this is one solution.
But this is the easiest because delta Y has a lot of.
I think
Cool.
because delta to Y. Then how do you divide up the currents? I don't know. I have to convert. Yeah. So since I'm not a circuits professor, I teach circuits to the non-double so that I only do simple voltage divider rule, current divider rule, KCL, KVL. So I like simple stuff. I like first order differential equation, nothing more difficult than that. Okay, so we calculated Vx. So how did we calculate Vx? Vx, they did it by V1 minus I2 R2. So it's Vx here, the voltage here, is equal to V1 minus this voltage drop, which is basically, this is 0 minus this voltage drop. It's I2 times R2, right? So that's where Vx came from. If I have Vx, then we said I can divide Vx by R3. So if I look at the polarity of the current here, the current's flowing from here to here. So it's 0 minus Vx over R3 is equal to I3. Okay, so 0 minus Vx, since I assume the polarity is this way. So I have 0 minus Vx over R3 is equal to I3. Then we solve for that from our previous solution of Vx. We just substituted here. And then we added up. So now I have I3 and I have I1 and 2 from before. I add them up to create I4. And then, we said that V output is equal to Vx minus I4 times R4. So we put this all together, simplify the equation, and we're left with this. Okay. So what was the requirement? The requirement was not to use a resistance more than 1 mega ohm in this circuit. That was the question here. Use the circuit to design an inverting amplifier with a gain of 100. So I want a large gain amplifier. At the same time, I want the input resistance to be 1 mega ohm. And I cannot use any resistor more than 1 mega ohm in the circuit. Right? That's the practical value. This is what I have in my shop. Right? So obviously the input resistance is 1 mega ohm. And I know that the input resistance is equal to VI over R1. VI over I1, which is R1 in this case. So I know that R1, I will have to keep it as 1 mega ohm, right? Since R1 here is the input resistance, then R1 will have to be 1 mega ohm. Because I want the input resistance to be 1 mega ohm. Okay, if I'm going to use a classical inverting amplifier, then its gain is minus R2 over R1. It means if this is 1 mega ohm, this needs to be 100 mega ohms to give me a gain of 100, right? A 100 mega ohm resistor is not something you can find practically. So if that's the case, or this is not something you have in your shop, so if that's the case, what do you do? How does this circuit help? Let's look at the gain equation that we derived for this circuit. The gain equation looks like this. This is V output over V input. So, and we already said that R1 is going to be equal to 1 mega ohm. Right? So this is 1 mega ohm here. R1 is 1 mega ohm. And I want this to equal 100 volts per volt. So, how do I go about this?
You need to assign value.
So if I choose, okay, don't read here, but
Oh, you need to-
canvas desktop banner. If I choose R2, I only have the biggest I have is 1 mega ohm, right? So if I choose R2 to be less than 1 mega ohm, right? Am I gonna get an increasing gain or a decreasing gain? Remember, I want a gain of 100.
Increase. This is large numbers and
No, it's gonna be less. So this is gonna be 0.5. Like this is 1 mega ohm.
oh,
This is the largest I can use. So I have to use something less. So let's say I use half a mega ohm. That means I'm decreasing the gain, right? So is that a good thing or a bad thing? No, it's not a good thing because I want a gain of 100, right? So obviously this is not going to help. So how about if I choose R2 to be also 1 mega ohm? So I made this 1. The stuff outside is 1, okay? At least I don't make it small so that I multiply it by whatever I came up with inside this brackets, I will multiply by something less than 1. If I do that, then it's not going to be, this has to be 500 for this to be 0.2, for example. I have to make a gain of 500 here, right? So I already sort of now fixed R2 to 1 mega ohm, right? So if I fix this to 1 mega ohm, one good choice is also to put R4 equals 1 mega ohm. If I do that, then I'm inside the brackets I have 1 plus 1. Plus, this was 1 mega ohm because I fixed it to 1 mega ohm here. Now I can do what?
Let's find out.
Just so-
I can make R3 small. Since it's in the denominator now, then this fraction will be large. So I can control the gain using R3. Right? The gain here is independent of, it's not independent of R1, but I'm able to make R1 large, as at the same time control the gain independently using R3.
So you got resistor, so you can.
Yeah.
But,
Yes, ma'am.
I'm confused about the negative sign.
You're confused about the negative sign. Why?
So that's
It's
the
an inverting amplifier. They want an inverting amplifier. So we derive, we just from the derivation, I mean, it happens to be an inverting amplifier. That's what they asked for it. Okay? Any questions on this? We're good? We understand the justification? It's described, what I did is described here, so you can go
But
through.
if you solve for R3, it will be negative. That's why I'm confused.
No, why would it be negative?
Because
So
of
the
the
negative
negative
one.
sign.
What?
You see the negative sign outside. when
Yeah,
you put
yeah,
some-
negative 100, fine. They want an inverting amplifier with a gain of 100. It means a negative 100 gain. Sorry, maybe I should have put this negative here. The negative has to stay because it's an inverting amplifier. They want an inverting amplifier. So, okay.
So if you solve for R3 now, it will be
Yeah. R3, this is 1. Outside you have 1. This is 1 plus 1. And then, so this is 2. 2 plus 98 is equal to 1 over R3. So you solve for R3. Right? So R3 will happen to be, they solve for it here. Yeah. R3 can be calculated to be 10.2 kilo ohm. Okay? So it's a nice example. I like this example. So, anyway. That doesn't mean it's on the exam. It's just something. Okay, so, and again, they also describe what we were talking about, the idea of amplifying the current. We said, if you put just an ideal current source here, I1 is equal to I2, and I'm adding whatever current in here to I1 or I2 to create a larger I4. They're just describing what I just discussed in the class. Okay, so now what can we do with something like this? So one application of the inverting amplifier is a summer. So you can add some signals, add some voltages together, add or subtract some voltages together using a circuit like this one. Yeah. So But again, forget I'm not talking about that more complicated circuit with the high input impedance. Just a simple inverting amplifier circuit, or the inverting amplifier configuration, which is what we have here. So this is our original inverting amplifier configuration was with a single resistor at the input. So I had one resistor. Typically, I forget about these two. I typically had one resistor here, and then the gain was what? The gain for, if I have R1 and RF, the gain was negative RF, or R2 over R1. In this case, it's called RF. They call it RF. So it's RF over R1. So this will be the gain for any input signal that I have here, right? And then, since I have an infinite input impedance, the same. I mean, it's the same. Basically, we're not. There's not a new derivation. What they're telling us here, or the new addition that they're adding here, is that they're telling us that superposition applies to such circuits that we have, that we're applying at the input of this op-amp. So if I put these circuits here,
Just add them all.
this is V1, this is V2, this is V3. So all of these will push a current into this branch. And this current is the sum of these individual currents. And this current will flow here. Hence, we have the same sort of gain effect that we had before. But to simplify our analysis, we can think of it as a superposition problem. Remember, we don't have any time-dependent elements. It's a linear circuit, right? I don't have any nonlinear elements that are changing things abruptly. I'm not saturating, I'm not clipping, I'm not cutting off. I'm just applying a linear gain, right? My gain was RF over R1. This is a linear gain, right? So since it's a linear gain, then I can apply superposition. At the input, if I have multiple inputs, I can apply superposition here. So I1 here is equal to V1 over R1, I2 is equal to V2 over R2, and so on and so forth. So I can write my output as what? V output is equal to, it's a negative inverting amplifier, right? What am I doing to V1? I am applying again RF over R1 to it. What am I doing to V2? Same thing, V1, V2, RF over R2, and so on and so forth. And that's what they have here. So it's a summing amplifier. I can also subtract and add numbers. So I can add and subtract as well. So the next example shows if I want to create something that looks like, if I want to add and subtract some terms, so I can build something like this. So think of it as what we just described now. So if I want to look at the gain for this circuit, how do I derive it? Let's look at the gain for V1 and V2. The gain for V1 and V2 is equal to what? I cannot put a positive supply, a negative supply in parallel, because current will flow. So if I put this and this in parallel, the currents will not sum up here, right? They will circulate between them only, right? So I cannot put a positive input and a negative input in parallel. So let's say now I put a set of positive inputs here and a set of negative inputs here, for example. So the circuit will, we'll apply the same superposition stuff that we discussed. So what am I going to see at the output here? What is the intermediate output? This intermediate output will be what? Yes, sir.
Is that a power supply?
Yeah, this is a DC power supply. This is a DC
So-
power supply, but one is positive, one is negative.
And they're the same.
The same or different does not mean.
And that would just cause it to circulate. into-
Current will just flow in here.
Okay.
Current will just flow in this loop. Yeah.
Will be negative current is RA over R1 times V1 plus R1.
Yeah. So the goal, So I will be applying the gain RA over R1 to what? To V1, and then I will see that here, right? I will not see that here yet, right? No, the V1 is positive. V1 and V2 are positives, and then these are negatives.
The equation itself is a negative sign.
Fine. Sorry, yeah, I should add negative. There's a negative outside. It's an inverting amplifier. Thank you. So minus V1 RA over R1, right? That's what I see until here. But again, there's a following one.
And this one is negative, so it's positive.
What do you mean negative?
This one,
There is a voltage output here. There's an output voltage here.
which is negative.
No, it's not negative. It's equal to
Negative.
for if I have only V1 input, fine. It's negative V1 over RA over R1. Yeah, I see what you're saying. Yeah, since it's negative, so then they're all negatives here. Yes, I agree. Sorry, I didn't understand what you're saying. I agree. So the output here is a negative value. So it's an inverting amplifier, right? But what is now the other gain that I will apply to this V1 signal?
Plus
RC.
Not plus, so because it's going to come here, and then I will apply another gain to it, RC over RB. Right? And then I will do the same for V2. RA over V2, RA over R2 times RC over RB. Right? So these two inputs will see the gain due to this stage, and then the gain due to this stage. How about these inputs?
This will be initially negative.
These inputs, yeah. So these inputs will see this gain only, which is RC over R3 multiplied by V3, right? And this one will see
RC over R4
RC over R4
times
times V4.
plus 10.
Yes, we will add them together. We'll put them all inside the parentheses. So they have that in the next down here in the slides, I think, or in the textbook. Yeah, here they have that here, right? So
But you see, these last two are negative.
negative and then another negative.
No, but these two are positive.
Sure, because they only saw one gain,
Yeah.
right? So the initial signals, the V1 and V2 were inverted, and then they were inverted again. So it became positive,
And positive. Yeah.
right?
And these guys only saw
Then these saw only one inversion. So then they became, so then they stayed negative. So if I want to add and subtract, this is something I can do. Of course, I have to adjust the gains to add and subtract whatever I want to add and subtract, so that I don't, add and subtract meaningful things here,
That's why we have
right? So this is another application of that. So yeah, you have the negative because of the stages. Yeah, two inverting ones. Okay. So any questions on this? And this is called a weighted summer. You can think of it, weighted summer, weighted subtractor. So. Okay. Weighted summer, exactly, just like this summer, exactly. You're weighted with, courses. Okay. So we discussed the inverting amplifier. Now we discuss something very similar. So the logic will be very similar to what we discussed for the inverting amplifier. We will discuss what is called a non-inverting amplifier. These are the two main families of op-amp amplifiers, right? Remember, the op-amp is an amplifier itself, right? But again, it has open loop gain that is huge, so it was not very useful for us to construct meaningful circuits. So we have two classes of amplifiers, inverting and non-inverting. The other main application for op-amp circuits is filtering. So filtering is a type of amplification, frequency-dependent amplification, right? At the end of the day, filtering means I want to pass a signal through and attenuate it at high frequencies, for example, if I want to filter high pass or low pass, right? So we are either going to be creating a inverting amplifier, non-inverting amplifier. We're going to discuss a difference amplifier. So maybe I will, the output from this one, output from this one, subtract them from each other. And we saw that the subtracting from each other thing, we saw sometimes is interesting when we have common mode, right? When we have common mode signal at the inputs of both devices, we saw that it may be interesting. So we will look at a difference amplifier as well, and then we will look at some other details of op-amps here. Anyway, so non-inverting configuration. So as the name implies, it will be very similar to what we did before, but the output will be a positive value. It will not be it will be one in phase with the input signal. If there is no other phase shift, I mean in phase meaning same polarity. Sorry, same polarity as the input. The phase may change depending on the frequency dependent of the frequency characteristics of the circuit here. So, and we will also assume the infinite gain assumption that we have, and we will also still use negative feedback, okay? So this negative feedback will be something that is very interesting and always useful for us, right? So this is the circuit. this is the circuit. Original in the inverting amplifier. Where did I put the input signal?
At the negative.
Yeah, in the inverting amplifier, the signal, the sensor was connected here, and this the non-inverting input was connected to ground. In the non-inverting amplifier, the input signal is connected to the non-inverting terminal, and this terminal is connected to ground. But the common thing is I still have negative feedback. If I have negative feedback, what does this mean? As soon as I see negative feedback,
It's gonna,
what does it mean? What's the restriction I have on these two?
voltage equals zero.
Not equal zero, equal to each other. The voltage between them, the voltage between them is very small or equal to zero,
Okay.
meaning that this node is at the same node as this voltage. Now, it just happens to be that this node is at VI. So this node is going to be at VI. So if this node is at VI, and I connect this to ground,
So the current.
current will flow this way due to VI on one side, this is VI here, and 0 here. So the current at V2, this is VI. So the current, this current here is going to equal to VI minus 0 over R1, right? So VI over R1 as we see here. Okay, that's this current. And we have the same assumptions of input impedance being infinite to the ideal amplifier, meaning there's no current flowing into this op-amp, into or out of the op-amp, right? For any practical purposes, there's no current. What does this mean? It means that this current, I1 here, is coming from this branch. It flows through this branch as well. So this is I2 is equal to I1, which is equal to VI over R1, right? So this is the same. This current here is the same as this current here, right? Now, what is the output voltage equal to? So this output voltage here, I do Kirchhoff voltage law. I go around the loop, right? KVL around the loop. So I have V output here. There's a current in this direction, right? And throwing in this resistor. So I have a voltage drop in the opposite direction, since I assumed current is flowing in this direction, right? And then I have a voltage here that I know, so I can stop, right? Because the voltage here is VI, so I can stop here, right? So V output is going to be equal to what? This VI is with respect to ground, right? So VI plus this voltage drop is equal to V output or V naught, right? So V output or V naught is equal to VI plus the voltage drop across this resistor, so it's VI over R2
That's the current.
time, which is the current, times VI over R1, sorry,
One, yeah. So times of two.
times R2.
I missed it.
It's okay. It's okay, as long as you're awake, I'm happy. So I can factor out VI, and I'm left with 1 plus R2 over R1, that is V output. So V output over V input, which is the gain, equal to 1 plus R2 over R1. Hmm?
R1 over R2 plus 1 over.
Yeah, or you can, common denominator, you can R1 plus R2 over R1. Right, okay, so this is the gain of this circuit. In volts per volts, or dimensionless terms, you can convert that to dB by 20 log this number. Okay, so this is the basic non-inverting amplifier configuration. What is the input impedance? Did I talk about that here? Yeah, what's the input impedance? They talk about it later, but since I asked the question, what's the input impedance? Guys, remember we said the standard way of measuring input impedance. What did we say yesterday? And today? No. Exactly. You apply an ideal voltage source to your block, to your circuit. Where is your circuit? Your circuit in this case is now all of this. This is the box, the black box. This is one terminal and this is ground. Right? This is your box. You apply an ideal voltage source here and you measure the current. Right? This is how you would measure it. So what current am I going to measure? And then our input is going to be this voltage that you applied divided by the current that you measured. So what is our input? Infinity, exactly. Because I assume that the current flowing here is 0 for an ideal amplifier. Later we'll see that it's not, but for now it is ideally infinite. Yeah. Okay. So this is a nice circuit then, right? I like the circuit because our input is infinite. I will not load my sensor. Right? The sensor will not be loaded. I will not be asking the sensor to provide me with current to be able to utilize it or to measure, to send the signal through the amplifier. So it's a nice, very interesting circuit. And the output voltage, the output impedance is measured the same way. So what is the equivalent circuit of the output? This is the op-amp equivalent circuit. The op-amp equivalent circuit is a dependent source resistance if it's available, and ground. Right? Here they didn't tell us it has an output resistance, so it's just a pure, it's just a source. Source, how do I measure? Again, how do I measure the output resistance? In the same way. I put a ohm meter here, which is basically an ideal voltage source. I measure the current flowing through and divide this voltage by this current. Right? What is it going to measure? There's no current flowing. This is not going to measure this. This will measure what? It will measure the open circuit voltage actually. It will actually measure the open circuit voltage. If there is current flowing, if you put the voltage, since there is no input, this voltage source is short circuited. If it's short circuited, if I put the voltage source here, a very high current will flow, right? Ideally speaking, of course, a multimeter cannot provide that. You would have to create an ideal voltage source, not an ohm meter. Ohm meter was the way I used to explain it at the beginning, but an ohm meter would not be able to measure something like that. So I guess an ohm meter, after a certain amount of current, I don't know how the ohm meter measures a short circuit. Like an ohm meter is basically an ideal voltage source, right? It supplies an ideal voltage that is known, and depending on the current that goes out, it will take this ideal voltage that they know divided by the current, and you calculate the resistance, right? But in this case, the current should be theoretically infinite because I don't have any impedance or resistance. So, but practically an ohm meter cannot provide infinite current. So I don't know how the circuit is exactly designed for an ohm meter. Maybe after some point, they decide that this is a very, very low impedance, hence short circuit. Yeah, right? Since they supply a very low voltage. If you supply a low voltage and the current is still high, they decide that this resistance is so small, I will just say it's a short circuit. Probably that's what it is. Yeah. So I will measure a large current. This large current, take a small voltage divided by a large current. It will be what? Small voltage divided by large current. So what is our output? Ideally 0. Right? So this is a nice device. It's a device that has infinite input impedance, 0 output impedance. So there's no effect on the loading that will change the voltage of the output. If I put whatever resistance here, I put a small resistor, large resistor, I will still not see a change in the output voltage, which is nice. So the output voltage will always be governed by R2 over R1 selection. It does not depend on anything else inside the amplifier. Right? So it's a nice circuit. And we will see. How else can you, so we derived equations, blah, blah. So you can easily also derive the output equation using voltage divider, right? So if this is an input voltage, this input voltage is placed across this resistor, it's series with this resistor to ground, right? So, and this resistor, this node here has a voltage of VI. So you can use nodal voltage analysis because you know that VI is equal to what? It's equal to V output times R1 over R1 plus R2. Right? So VI is equal to V output times R1 over R1 plus R2. Just from nodal analysis. For the potential divider between here and these two, between this source and these two resistors. So you can do it that way as well. Yeah. Same effect. Okay, so now let's see. So now, like we did before for the non-inverting amplifier, for the inverting amplifier, we looked at the effect of here we looked at the effect, the gain of the amplifier with an infinite open loop gain op-amp, right? So we calculated the gain to be 1 plus R2 over R1. The assumption was what? The assumption was
Current is
that the voltage difference between these two is zero because of the feedback, but also if the voltage difference between these two is zero, so the output voltage V output is equal to A times V2 minus V1. This is V2, this is V1. We assume that V1 is equal to what? VI, right? So it's equal to A times VI minus V1. So V1, let's solve for V1. If this is finite, then V1 is equal to, so V output over A,
Isn't V2 minus V1 equals 0?
V2 minus V1 equals 0. Yeah, because of the negative feedback. So, yeah, because of the negative feedback, it's equal to 0. The difference between them is equal to 0 because of the negative feedback, I agree. So V output is equal to, the open loop gain is equal to 0, yes, but one second. It will be driven to 0 if I assume that this is infinite gain. Remember the calculation, the circuit that we did before? Having the feedback will drive it to 0. Or something depending on the gain, the value of the DC source. Remember we had two sources? A resistor here and a source. And a resistor here with another source. Right? So I can drive this voltage to 0 if I do what? If I make these two resistors equal and I make these two sources equal, for example. But if I make this resistor very small, I need to make this voltage source what? Smaller, because if I make this small, there is less resistance to the voltage in the circuit, so more current will flow, then a larger voltage drop, which opposes this source, right? So I can make this large, because remember my gain was, 1 plus R2 over R1. So maybe I made R2 large. If I make R2 large, then there is more impedance to current flow in this circuit. Then what do I need to do? I need to make this output voltage larger to be able to drive it. So this, assume that this is like a large source. We always assume that this is very large. Yeah. So that assumption is okay. It's fine in most cases. But what did it mean for the inverting amplifier, not the non-inverting? For the inverting amplifier, the inverting amplifier circuit looked like this. This is plus, this is minus. And then I had the signal, this was connected to ground. And this was a resistor here. And this was my feedback. This was my inverting amplifier. And I had plus minus V output here. A V2 minus V1 was equal to 0. And then V2 is also equal to 0 because it's grounded.
So it was a very negative.
So A times negative V1. So A times negative V1 is equal to V output. Right? That V output was equal to A times the differential gain. Right? So this is V output. So
why is
what?
number 5 on the,
5.
why is that one? Yeah, why is that one B? Is that BF or
This
VI?
one? That's VI.
Well, why isn't it V out divided by R2 the current?
No, because okay. So here I was describing something different. Okay, but let's go back to this one. Here, because of the feedback, the voltage difference between these two is virtually 0. So there's like a short circuit, meaning the voltage here is VI. If the voltage here is VI, what is the current flowing here? VI over R1. And since there's no current flowing in or out of the op-amp, then this current is going to come from this, through this branch and flow through R1.
Okay.
Okay, that's why this is the case. Okay, back to our inverting amplifier. This is the non-inverting. For the inverting amplifier, the open loop gain times V2 minus V1 is V output, correct? Which means that the V1 is equal to V output over A, minus V output over A. What did we assume A was? Infinite. Since we assumed A was infinite, then V1 was 0, so that's, which is confirming what we are saying here, that the difference between these two is 0, hence this is equal to this. Same thing for this case. This was 0. Since I have feedback, and I assume that the A is infinite, then this, from our calculation, is also 0 volts, right? That's the assumption that we came up with here. Yeah. So, but then we derived the case for the voltage here equal to V minus V naught over A, where A is a finite number. And that gave us a different gain that was not equal to minus R2 over R1. It gave us a different gain. You can go back to that if you want. Effect of finite gain. Yeah, finite open loop gain. This section. This is what I'm talking about. So here, in this case, we assume that this is not 0, it's minus V naught over A. Right? So, and then we came up with a gain equation. This gain equation on the numerator is minus R2 over R1. And something else came up in the denominator. If I make A infinite here, what happens? This term goes to 0, and I'm left with 1. So the gain will be minus R2 over R1. Same as before, which means you're correct. So we're going to do the same for the non-inverting amplifier. Because in practice, and we will see that very soon later in this chapter, the gain is actually a finite number. Right? So since the gain is a finite number, we have to figure out how it will affect my output voltage here. So that's what we are doing in this section. They actually don't derive that here. For a bonus, derive that. I derived it here. So for a bonus, derive this, and you get a half-point bonus on the class grade. So derive this. Okay? Derive the finite gain.
So 0.5% of the total.
Yes, 0.5% of the total grade bonus. Okay, so derive this. I know it works, so I derived it. So derive it. I mean, it's not in the textbook. Okay? If you don't, I mean, next class I can derive it in class if you have a problem with it. Yeah. Okay, but it's if you follow the same steps, basically, the voltage difference between them is going to be, not 0 in this case, right? Like the previous, it's the V1 will be equal to V output over A, and then you start working that way.
Tomorrow?
Yeah, for tomorrow. Right. Tomorrow is like in typical weeks, in typical semesters, like 2 days later, right? Huh? Fine, Thursday. Fine. Tomorrow's what? Wednesday?
Yeah, because we have lab today.
Thursday. Remember, we canceled the lab quizzes, but the pre-lab quizzes. We canceled the pre-lab quizzes. Yeah. I mean, you suggested. I'm fine with that. Huh? What? You want to cancel everything else? Huh? We'll work on that. Anyway, so if you calculate the trick again, the trick is you utilize V1 equal to V output over A, not 0. That will be what you're gonna be. That would be the so Vi minus, so here Vi minus V1 is equal to V output over A, where V1 will be a value. It's not going to be, Vi in this case, right? Here, ideally, it's what? Ideally, V1 is equal to Vi, right? In this case, V1 will have a value. This value is derived from the knowledge of the open loop gain equals the open loop gain multiplied by V2 minus V1 is equal to V output. That is the output equation. V2 is equal to Vi. Correct? This is V2, it's equal to Vi. If I assumed that there's 0 volts difference between these two, then V1 is also equal to Vi. That's if I assume that. But if I don't assume that, and because I assume that because of the fact that I have an open loop gain that's infinite. If I don't assume that, then V1 will have a value. V1 will have a value that you can calculate here, and it will include the finite gain value of A. Right? So that's what you need to derive, and show me on Thursday. You will end up with this. Again, do the same trick. Bring A to infinity. What happens to this gain?
It becomes
1 plus R2 over R1, which is what we derived before for the non-inverting amplifier. Right? So that's same thing we did before. Input resistance, we talked about the input resistance. What was the input resistance for the non-inverting amplifier that we see here? Input resistance.
Okay, it was infinite.
Exactly, since there's no current flowing in here. So the input resistance is infinity. And another application of this is, what if I do this? What if I make, so this is my output equation is equal to, my gain is equal 1 plus R2 over R1. If I make R1 go to infinity, and I make R2 go to 0, what do I get? The gain will be 1, right? So, and this is called the voltage follower circuit. So if I just want the input and output to follow each other, but I want the output to follow with a higher current gain, for example, not voltage gain, right? So if I want, sometimes you want that. Sometimes you have your sensor, and you want to send your analog signal to your ADC. And you don't want your ADC to sync current from your sensor. So what do? You just put a voltage follower in the middle. It's a unity gain non-inverting stage. So it's just an application of that. They have a separate section on that in the textbook, just because it's a very common circuit. So this is they have a separate section talking about the voltage follower. It's a basically unity gain amplifier. And it's R1 is infinity and R2 is 0. And because it's so common, it has, they've dedicated a small section to it here. Okay, voltage follower thing. But of course, we will talk about this later in the chapter. We will find, even though this is a voltage follower and we have external power supplies to supply the current flowing through this output branch, any device is current limited. Any physical system is current limited. So ideally here, according to this schematic, or according to this model, fine, this is an ideal voltage source that will produce as much current as you require, right? But of course, practical op-amps, and I'll try to, in next time, maybe I'll try to dig up a data sheet when we talk about the limitations. And any device, it's a physical system. You've manufactured this thing on a chip, right? You cannot have infinite current flowing through anything, right? Only superconductors can allow infinite current to flow, right? So this is not a superconductor, it's silicon. So silicon means it has voltage drop. It has voltage drop means it's a power loss. It has power loss, it means that it's heat. There's heat, that then it's at some point it will burn, right? So everything has a current limit, right? So this is something we'll talk about later, but it's not coming from the equivalent circuit. It's coming from the the manufacturing process itself. Yeah. So the next amplifier application we're going to talk about is called the difference amp. So we talked about inverting, and we talked about non-inverting amplifiers. We will talk about something interesting because when we talked about amplifiers, especially if you look at, for example, the gain for the equation that we have. So the gains for the two configurations that we have were what? The gain for the non-inverting was what? 1 plus R2 over R1. And the gain for the inverting was minus R2 over R1. This was what? V output over V input, right? What if V input contained some noise? Even without common, what if it contains some noise? One way is to find, you can filter. Or another way is to maybe find a way to put this noise on another circuit, for example, or another terminal, or the other terminal of the op-amp. And since the output basically subtracts the terminals from each other, then at the output I can see 0, like what we did for the common mode signal, for example. Yeah. So something like that is something that may be interesting from an application perspective. Yeah. And some sensors are also not referenced to ground. So sometimes you want to measure something that is not referenced to ground. So a transformer, for example. A transformer is not referenced to ground. A transformer actually is referenced to, you can build a circuit around the transformer. Let's say you have if you have your input AC here, and then you remember your rectifier circuits. You studied rectifiers, right? Full bridge rectifiers in 214. Okay, so okay. Let's you know what a transformer is? Where did you study transformers before? Not yet. Not yet. So a transformer is a device that converts voltages and currents from one side to another set of voltages and currents on the other side, while preserving power. Fine, there's some power loss.
Mutual inductance, this looks like.
No, it is not. It's not mutual inductance.
Does it convert AC to DC?
No, but it's an AC device. It's only used. Okay, but any inductance. Okay, we'll wrap up with this, explaining what this is. So, if I have a number of turns, right? And fine, for simplicity, I have a single turn, right? If I have a single turn, and I put this single turn in a time-varying magnetic field, so I have magnetic field that is changing sinusoidally, for example. I have a magnet here, for example. I put a north pole and a south pole, and I put these on a motor, and I keep turning these around. The magnets, right? Each point, right? So, for example, if the magnets are here, the magnetic field is going to go. How the magnetic field lines will go from north to south, and they will do this, right? Right? How about if the magnets are tilted? Same. The magnetic field lines will do this, right? So if I have a stationary turn here, right? Each side of this turn is a piece of wire. This piece of wire is in a magnetic field. If the magnets are on top of the wire in this position, there's a certain value of magnetic field that is cutting or linking this line. If the magnets are in a different position, right? The magnetic field that was seen here, the magnetic field vector now is on the side. It's sideways, so you can divide it up into one here and one here. If the turn is still perpendicular to, if the turn doesn't change position, and the magnet is the one that changes position, right? The component that is cutting the turn perpendicular to its cross-section area is going to change in value, right? Because it was originally perpendicular, so all the magnetic field is going through this turn perpendicularly. If I turn the magnets to one side, then this turning to one side causes a component to be in this direction and a component to be in another direction. This other direction component is not going to actually cut my turn at all. It's not going to link my turn at all. Right? So it's a different value of magnetic field. And you keep doing this, meaning you have a time-varying magnetic field that is cutting or crossing a turn, or linking a turn. What did Lenz's law say about this? If you have a time-varying magnetic field that is intersecting or linking a turn. No, you have a magnetic field, not electric field.
What's the problem?
You will have a time-varying magnetic field. If I write d phi by dt, maybe this makes things nicer. Look, no? Physics.
Gauss.
Huh? Doesn't ring a bell, the d phi by dt? It rings a bell, for sure.
Yeah, isn't it?
Dr. Athman, I'm sure, rang this bell before. How about Orbelich? How about maybe he used this, n d phi by dt?
And then there's a
The number
negative
of coils.
Sure, maybe the negative sign, that's okay. What else? So what did this equal? This is the most important one for me. Huh? Not integration, no, not integration.
I will equal n is the number of coils.
Sure. Here I have one coil.
Divided by dt.
Sure. It is equal to E. It's equal to a voltage that will be developed across this turn. Not electric field. It's a voltage. Fine. A voltage can produce an electric field. That's fine. A charge produces an electric field. But anyway, so E equals n divided by dt. Right? So there's a voltage developed across the turn because of the time-varying magnetic field. So a transformer will have many of these turns. Right? It's many of these turns. So you will put a voltage here at the input, this voltage will cause, again, it's time up? Okay, so we'll do this next time. inshallah. Good luck on the exam. Let me know if you have questions. Yeah.
Will you be with us?
Be with you.